Let us start the lecture. And our topic for today is functional limit theorems for continuous time random walks. Or continuous time random walks. The problem is the following. We know from the previous lectures the Donker theorem that if psi k are ID means zero, finite variance, then scaling limit of a random walk is a Brownian motion. So if we consider this process, then we have convergence in distribution to a Brownian motion. And we consider this process in the space of continuous functions with topology of uniform convergence on compact sets. I would like to recall that S psi of n is psi1 plus psi2 plus psi n, and we extend Sn to all non-negative t by linearity. So this is 1, 2, 3. So we have so the path approximately like this. Today we consider another problem. Assume that jumps of the initial random walk occurs not at integer numbers. So you wait 1 second and then Sn as xi make a jump. Assume that the time between jumps is random. The problem is the following. So let xi n and eta n be xi k and eta k be independent, identically distributed random variables. They may be dependent. Xi k are the same as before. So expectation of xi is 0. Variance of xi is, or xi k is sigma squared. And we assume that eta k are positive. Eta k are positive with probability 1. Now let us consider the following process. It's easier to make a picture than to write a formula. So let's mark here point eta 1. So this distance is eta 2. This distance is eta 3. This distance is eta 4. So actually this point is S eta of 1. This point is S eta of 2. This point is S eta of 4. Well, I use notations as before. S eta of n is eta 1 plus eta n, and S psi is psi 1 plus psi n. And now this distance is xi1, then take this distance xi2, this distance is xi3, and so on, xi3 and so on, and make the following picture. And here, okay.
I'm sorry, Xi I or S Xi I?
Oh,
Uh,
could you please repeat?
This point,
So this point is S psi of 2.
uh, does we
So this jump
oh,
is
okay,
psi
sorry,
1,
I haven't
this
seen the
jump is
graph.
psi 2, this jump is this, okay, not jump, I consider only continuous process. So this distance is psi 4, so this point is psi 2, psi 3, psi 4, S of psi 4,
Okay,
yes.
okay, thank you.
And the problem, well, and I denote this process by x of t. And the problem that I want to discuss is the following. Is there a scaling limit of x and t divided by square root of n as n goes to infinity? So what is the limit of this? Okay, and well, now let's think about a little bit about this picture. So this picture looks like this one. So if eta 1 is equals eta 2, eta 3, then we have the previous random walk. And is it possible to obtain this graph from the previous one? The answer is yes. The answer is yes. And again, it's easier sometimes to make a picture than to write a formal calculations, but then I will give rigorous formula also. At first, let me make a picture of S eta of t. So this point is 1, 2, 3, 4. So S eta of 1 is equal to eta 1. And recall that we extend this function by linearity. S eta of 2. So this is increasing process. So this distance is eta 2. Again, somewhere this distance is eta 3. Then, oops, this distance is eta 4. So S eta of t is a piecewise linear and continuous function, and S eta of t is strictly increasing. And observe that this process x of t is x psi of inverse function of t. Indeed, this function is continuous piecewise linear. S psi is continuous piecewise linear. So their composition is continuous and piecewise linear. What is the process S eta, so inverse of S eta? So we use this picture. So the result is this: 1, 2, 3, 4. Is this? We wait at 1 units of time, and the inverse of eta 1 is 1. So just look at this graph, make a symmetry with respect to bisectors of the first quadrant. Well, then you wait eta 2, and position is 2. Then you wait eta 3, and the value is 3, and the inverse function is linear on this, and so on intervals. So actually, this point is this, point is this point is this point is this, and then what is S psi of S eta inverse at this point? It equals S psi of 1. So this. If we take time this and we calculate inverse, the inverse is 2, and the value at this point is S psi of 2, and so on and so forth. So we see that indeed x of t is equal to composition. Okay, let us continue. We have this formula, and we want to investigate Donsker scaling limit. So we consider a x of n over square root of n. So S psi of inverse of nt divided by square root of n. Let me recall you that S psi of nt over square root of n converges to sigma times Brownian motion. We have S psi here. We have square root of n in the denominator, but we do not have n times something. So let's multiply and divide. S psi n times S eta of nt inverse divided by n divided by square root of n. And now two ideas. If we know that this function converges to some process, if this sequence converges to some process, then probably S psi of n times this divided by square root of n will converge to sigma times b, not at t, but at the limit point. Okay, so the first question is what is the limit of S at inverse of nt divided by n? So in which sense converges? What is the limit? I don't know, but it's reasonable to study this problem at first. Well, but maybe before investigating limit behavior of the inverse process, so this is zero question, is to find a limit of a random walk divided by n. And the first result is about limit of this sequence if eta k has the finite expectation. Oh. Theorem 1 is this. Assume that eta k are independent, identically distributed random variables. Eta k are positive with probability 1, and expectation of eta k is A is finite. The first part is the sequence of processes as eta of nt over n converges almost surely to the process at in the space of continuous functions with the topology of convergence on compact sets. So this sequence, so I state that this sequence converges here locally uniformly, and the second part of the theorem is convergence of inverses divided by n. Also converges almost surely to the process t over a, to the function t over a, again in C0 infinity. Before, so what do I know? I know, so idea is this. Actually, it's easy to guess the answer because by the law of large numbers, I know that S, okay, and T, well, for example, if we consider integer part of n t divided by n, is S of n t divided by nt integer part times integer part of nt divided by n. So this, by the law of large numbers, converges to A almost surely, and this sequence of functions converge to T. So the product converges to AT almost surely for every fixed T. To be honest, so let me write it like this, that probability of this event is is 1 for every fixed T. I need to move this quantum inside. So this is the first step. And I also need to show locally uniform convergence. So here we have only pointwise convergence. So we are not sure, maybe. So is it locally uniform or not? And next, I would like to discuss a result from mathematical analysis. So there is no randomness. The result on convergence of functions. And I will use this result quite often. Assume that Fn be a sequence of non-decreasing functions. Let be a sequence of non-decreasing functions from 0 infinity to R. And assume that that for all t, there exists a limit of Fn of t where f is continuous. Excuse me, not for all t, but for all t from the dense set from 0 infinity intersected with q, where f is continuous. And then Fn converges to f locally uniformly. Then for every t greater than 0, limit as n tends to infinity, supremum t in 0t, Fn of t minus f of t is 0. Well, sometimes I will write that Fn converges uniformly on 0t to f. So this is just notation that I will use sometimes. Proof. Well, I need to show this converges for every t, so without loss of generality, I may assume that t is natural number. Otherwise, I will consider larger interval, not 0t, but 0 integer part of t plus 1. T. Oops. This is time. And this is, so let this be the graph of y is f of t. And all functions fn were non-decreasing, f is its limit and it's continuous, so it's easy to see that fn is non-decreasing also. Now, let epsilon be fixed. This limit function f is continuous. I want to find numbers t1, t2, and so on, tk minus 1, and t is tk, such that increment on each interval 0, t1, t1, t2 of the function f is small, is less than epsilon. So find t1, t2, tk, find k and t1, t2, tk such that for every k, for every, sorry, j between 0 and k minus 1, such that f of tj plus 1 minus f of tj is less than epsilon. So this is possible. This is possible because f is continuous, and hence it's uniformly continuous. Well, then let me estimate f of t minus f n of t, absolute value. Okay, assume that this is interval tj plus 1, and assume that t is here. And what do I know? I know that f at this point is greater than f of t. F of tj is less than or equal than f of t. And I know that fn converges to f at this point and at this point, because I know that we have convergence for all rational numbers. So let us add and subtract.
I'm sorry, should we write that this TK is from our dense set?
Yes, right, rational. Certainly, you're right. Such that, so maybe I said this, but I forget to in Q.
And
Yes.
it even can be not rational, but any dense set. Yes.
I told you that without laws of generality, we may assume that T is rational number. Otherwise, we take integer part of T plus 1. And if we prove uniform convergence on greater interval, then you have uniform convergence on smaller interval. So without loss of generality, we may assume that T is rational also.
Okay, thank you.
Okay, now we add and subtract, and oops. Oh, so less than or equal to. Less than or equal to So f of t minus f of tj plus 1. Okay, so I assume that t in tj plus 1 plus f of tj plus 1 minus fn of tj plus 1 plus, so I subtract, so I have to add or maybe I do, oh, sorry, I do, excuse me, so I do the following trick. So less than or equal to, at first, let me write like this. Less than f of tn plus 1 minus f tj plus 1 minus f n of tj plus 1 plus f n of tj plus 1 minus f of fn of t. Okay, so this is true. So I replace this by the larger number and I add and subtract. So this is correct. This is correct.
Uh, and absolute value, yes?
Sorry?
We should add absolute value or not?
Well, at first I want to just write inequality for ft minus fn and then for and then for this. Okay.
I think we can make it in one time because use absolute value and the triangle inequality. So uh, I think we can make it in immediately.
Maybe you are right.
And we don't know that ft is bigger than fn of t.
Yeah, I don't know which one is larger and which one is smaller. Okay, another inequality. So if I consider here smaller value, then this is smaller and with minus it's larger. And now again, let me add here and subtract f of tj plus 1 minus plus f of tj plus 1. And here I add and subtract f of tj. Okay, just equality equals f of tj plus 1 minus fn of tj plus 1 minus fn of tj plus f of tj and plus f of tj plus 1 minus f of tj. Oh, okay. Well, this and this cancels out. So we have the inequality f of tj minus fn of tj, and this is less than epsilon, plus epsilon. And I can write even more that this is less than absolute value, and it can be shown similarly that minus f of t plus fn of t is less than, if you make similar calculations, then you will see f of tj plus 1 minus fn of tj plus 1 also plus epsilon. If we combine these two inequalities, then we get the following, that f of t minus f of t fn of t absolute value is less than or equal to maximum of this and this, and f tj plus 1 minus fn of tj plus 1 plus epsilon. And now take supremum over all t in 0t. Actually, there is no t in the right-hand side, so this supremum is less than or equal to maximum over all j between 0 and k minus 1 of maximum of this as epsilon. And now we pass to a limit in the right-hand side and the left-hand side. Well, I don't know if the limit exists, but the upper limit of this is less than or equal to upper limit of this. And there are only finite number of numbers under the maximum sign. And we know that for each j, we have convergence. So the upper limit of the right-hand side is epsilon. So we have proved that the upper limit of the corresponding supremum is less than or equal to epsilon, and epsilon was an arbitrary positive number. So what does it mean? This means that the limit exists, and this limit is equal to, and the limit is equal to 0. And the lemma is proved. Okay, questions?
Sorry, I want again the same question. I meant when asked like the last time, not the tbig should be q. I asked in general, not in the proof, in the statement of lemma. I suppose we can consider any dense set
Yes, you
of.
are absolutely right. So
Okay.
you may consider here any dense subset of R plus, yes, of positive part of the real line.
Thank you.
Yeah, you're absolutely right. And now let us return to this state. So we want to prove that probability that for every t greater than 0, limit of s eta of nt over n minus at, supremum t in 0t, is 0 with probability 1. At first, I will use the following okay. At first, I know that for every t small, s eta nt divided by n converges to at with probability 1. Indeed, s of n, s eta of nt over n is greater than or equal to s eta of integer part of nt divided by n. Recall that eta is non-negative, less than or equal to s eta of integer part of nt plus 1 over n, and we multiply and divide by this number, nt plus 1, nt plus 1, and here we multiply and divide by integer part of nt. This converges to t, this converges to t, and by the law of large number, this converges to a almost surely. So the product in the left-hand side and in the right-hand side converges to product a of t. So we have this. We have this. Now, to prove this statement, it's sufficient to prove that we have convergence. Okay, zero star. So to prove star, it is sufficient to verify that probability that for every t rational non-negative number, limit of s of nt over n is at with probability 1. We have this, And we have this. This event is smaller than this event. This is intersection of this. And again, today and in our course, we will often use the following result. If for every n, probability of an is 1, then probability of intersection is also 1. And if t is fixed, this event has a probability 1. And here it's written a countable intersection. So if I know this fact, then this fact immediately follows from this. And well, this fact is easy to check indeed. Probability of intersection is 1 minus probability of union of the complements is equal to 1 minus sum of probabilities. Oh, no, is less than or equal. No, excuse me, not less than or equal. Greater than or equal to 1 minus probability, sum of probabilities. Well, this guy is less than sum of probabilities. So with minus, we have opposite inequality. And probability of this event is 0. Sum of zeros is 0. So the result is 1. So probability of intersection is greater than or equal to 1. Well, we know that this number is less than or equal to 1. So we have proved this, and consequently, we proved the first part of the theorem. Questions?
No questions.
Excellent. So now the first part of theorem is proved, and we continue. And now we need to show the second part of theorem. And well, you see convergence of certain functions, and here we see a statement about convergence of their inverses. So my next result also has a deterministic nature. It states that if sequence of non-decreasing functions converges locally uniformly, then the sequence of their inverses also converge locally uniformly. So let me formulate the result. Excuse me. Yes. Okay. Let Fn be a sequence of functions that are continuous. Second, strictly increasing. Third, Fn of 0 is 0 and they're unbounded. So let me write this like Fn of plus infinity is plus infinity. And the first item is for every t positive, there is a limit. Fn of t is f of t. And well, also assume that f has this property. Let be seen. And f be such that, and also f of 0 is 0, f of plus infinity is infinity, fn and f, okay, fn and f are strictly increasing and continuous. Then sequence of inverses converges locally uniformly to inverse of f. This is lemma to locally uniformly. Well, we know that actually this item 4 implies that we have locally uniform convergence. So it suffices to prove that we have pointwise convergence. Moreover, that we have convergence for even more for rational numbers. So we need to show that for every t greater than 0, fn inverse of t converges to f 0 t, and apply lemma 1. Oops, and here just f. Okay. I would like to mention that since all functions are continuous and strictly increasing, then inverses, and the third condition, then inverses are also continuous, strictly increasing. They start from 0, they are unbounded, they're defined for all t. So these objects are well defined, and we have locally uniform convergence on 0 infinity. Uh, well, okay, let t be fixed, and let S be the inverse of t. So f of S is t, S is positive. Uh, mm, let a number S, okay, S plus be greater than S. Then f of S plus is greater than f of S. I know that limit Sn tends to infinity, fn of S plus, okay, is equal to t. is equal to f of s plus is greater than or equal to t. And moreover, I know that strictly greater than t. So if this sequence converges to this number, and this number is strictly greater than t, then there exists n0 such that for sufficiently large n, fn of s plus is greater than t. Consider inverse, fn inverse of left-hand side and of the right-hand side. You know that inverse is increasing function. So we see that s plus is greater than the inverse fn inverse of t. Hence, pass to a limit in the left-hand side. In the right-hand side, I know that s plus greater than or equal to upper limit of inverses of t as n tends to infinity. So we proved that for any s plus which is greater than s plus is greater than this. Hence, this inequality and arbitrarity of s plus yields that s is greater than or equal to upper limit of inverses. And similarly, it can be shown, so exercise, it can be shown that the lower limit of inverses is less than or equal to s. And s is inverse of t. So to solve this exercise, we have to select arbitrary s minus, which is less than s, and consider inequality, take inverse, and so on and so forth. So the inverse is greater than upper limit, and so the inverse of t is greater than upper limit of inverses. And, excuse me, opposite inequality, and less than lower limit. So the limit exists and is equal to the inverse, and the lemma is proved. And now we return back to our theorem. We have convergence of these to AT, and we have to prove that the scaling limit of this is equal to T over A. The only thing I need to verify is that this function is really inverse of this function. So actually, this is composition of this function nt and divided by n. Okay, assume that we have a function f. It assumes that it has the inverse. So assume that f is continuous, strictly increasing. There is inverse function, and assume that assume that A and B are positive numbers. And I would like to find the inverse of function f of AB, or f of AX divided by B. Well, B's function is continuous and strictly increasing, so the inverse function exists. So how to find it? So I need to solve equation. So I have to find x as a function of y. So by is equal to f of ax. So inverse of by is ax. So x is inverse of f taken at the point by divided by a. So corollary, the inverse function of f(ax) divided by b is f inverse of f at the point bx divided by a. And in this theorem, a is n, b is n. And so the inverse of s eta of nt divided by n. Okay, so this is not 1 divided by, this is inverse function is equal to this. And we know that this function converges to at, and inverse function of a times t is t divided by a. So by the previous lemma, we see that this converges to ta as n converges to infinity with probability 1 locally uniformly. And the theorem is proved. And I wish to recall you the first question. Now we consider this sequence, and I know that this converges to t divided by a. So what is the limit of Donsker scaling limit of continuous time random walk x? So it should be, so this is a question, but this is a guess, and actually this is true, that the result will be sigma times Brownian motion at the point t over a. Or apply self-similarity of a Brownian motion, okay, the same distribution, b of t. And this is result, and let me formulate the theorem. Assume that psi k eta k are ID. Psi k have zero mean and finite variance, and eta k are positive. Expectation of eta k is a, is finite.
Excuse me, you have written here 2 times. D.
Var, yes, variance. Thanks. Then scaling limit of x and t divided by square root of n is sigma over square root of A. Okay, A is finite. Times a Brownian motion, and we consider convergence in distribution in the space of continuous functions with the topology of the uniform convergence. Okay, so this was a guess. So we don't know. We know that these processes converges almost surely to this linear function, and we know that scaling limit of s psi n s divided by square root of n converges in distribution to a Brownian motion, but it is not clear that sequence of compositions also converges. But let me recall you the Skorohod's representation theorem and certain facts from the theory of weak convergence. We know that s psi of nt divided by square root of n converges in distribution to sigma times Brownian motion. We also have proven that this sequence of inverses converges to t divided by a locally uniformly with probability 1. Well, we can write that it converges in distribution in C0 infinity. And this process, this element of C0 t is non-random. And we discussed that if one sequence converges to a limit in distribution and another sequence converges to a deterministic point, then you have convergence of pairs. So you have convergence in distribution of sequence of pairs. Okay. To sigma Brownian motion and t divided by a in the product space in C0 infinity times C0 infinity. And C0 infinity is complete separable metric space, and the product of C0 infinity is also completed separable metric space. So by the Skorohod representation theorem, there is Skorohod representation theorem. There is a sequence of copies of these random variables s psi, okay, with tilde and with index n. No, not n. Okay, yes, with index n of nt divided by square root of n and copies of these. I need to write index somewhere else. Okay, n here of nt over square root of n and as at n inverse. So this index n means that this is a copy of this. divided by n. So the distribution of this and this distribution of this are equal, and this sequence converge to sigma times some Brownian motion, comma, and t divided by a. Almost sure. And this is a sequence of processes that converge locally uniformly. And small exercise for you. If Fn converges locally uniformly to F and Gn converges locally uniformly to G, and then, well, and the image of Gn take values in domain of definition of F, and all functions are continuous, then the sequence of compositions converges local to a composition locally uniform. Locally uniform. So this exercise implies that you have almost sure convergence of compositions n S inverse eta n and t over n, okay, n is cancelled, over square root of n to sigma b, and composition with the second function t over a, almost surely in local uniformly, so in C0 infinity. So this sequence, it has the same distribution as our initial scalings of x, converge almost surely to this process. Hence, x of nt over square root of n converges in distribution to sigma Brownian motion of t over a. And we use self-similarity property of Brownian motion. This process has the same distribution as sigma over square root of a times b of t. And the theorem is proof. Thank you for your attention. Questions?
So we go back to our original processes. They distributed the same.
Yes.
And if copies converge in distribution, then original should converge in
Yes.
distribution.
Yes.
Okay.
Because Igor, what is the definition of convergence in distribution? So zeta n converges to zeta in distribution if for any f bounded and continuous, expectation of f of zeta n converges to expectation of f of zeta. And if zeta n tilde is a copy of zeta n, and if zeta tilde is a copy of zeta, then expectation of f of zeta n tilde and f of zeta n coincide.
Okay. Yes, thank you very much. Yes, it's literally just in terms of distribution, which is the same.
Yes, and we know that convergent that if you have almost sure convergence, then you have convergence in distribution.
Yes. Thank you very much. It's clear.
Today we applied, you see, we applied Skorokhod representation, and we reduce our theorem to, so we do not consider convergence in distribution. We consider only almost sure convergence, like in mathematical analysis. And I thought about convergence in distribution as convergence for every omega, and Skorokhod representation theorem helped me with this. Maybe a small remark. You see that we need many results from mathematical analysis about inverses. Well, this exam exercise about compositions and so on and so forth. And I recommend you the book of Witt. I forget the name. I will send you the title of this book in Telegram. And in his book, there is a chapter that is called Useful Functions.
It's called
And
plastic,
Process limits and applications.
yes, exactly. Yes. And in this section, useful functions, he considered all of them, like addition, maximum, inverse, composition in different topologies. And he also proved continuity under some assumptions of these maps. Okay, any other questions? If no, thank you for your attention and see you next week.